Greetings and welcome to lecture number 23 of the course Introduction to Fourier Analysis. On the previous lecture, we completed our discussion on tempered distributions. We showed that tempered distributions, convolution, and the Fourier transform interact in the expected way. The Fourier transform of the convolution between a tempered distribution lambda and a Schwarz function phi coincides with the tempered distribution hat phi times hat lambda. This may seem like a fairly abstract result, so the purpose of this lecture is to give a concrete application. To be honest, after seeing this lecture, I'm not sure if you will agree that the application is very concrete. But it certainly will be an application of Fourier transforms and tempered distributions to a problem where these concepts are not visible to begin with. This problem lies within the theory of singular integral operators. Discussing the general theory and applications of singular integral operators would take another course, or actually several courses. For more information, I recommend Elias Stein's book Harmonic Analysis. For now, we will concentrate on one specific singular integral operator, the Hilbert transform. In order not to drown you in the technical details immediately, this lecture will begin by a slightly informal and not completely rigorous discussion. The further you watch, the more precise it will get. As we mentioned, the Hilbert transform, usually denoted by capital H, is a prototypical singular integral operator. It takes a complex valued function f defined on the real line and transforms it into another function hf by the formula hf of x equals 1 over pi times the integral over r of fy divided by x minus y dy. Don't worry at this point whether this integral is well defined. We will return to this point later. Looking at this formal expression for the Hilbert transform, you should, however, recognize the presence of a convolution. The expression above equals the convolution of f with the function 1 over pi z, evaluated at the point x. This function 1 over pi z is known as the kernel of the Hilbert transform. We will denote it here by a capital K. Why is the Hilbert transform called a singular integral operator? The reason is that the kernel K is singular, in the sense that it is not absolutely integrable, not even locally. The integral of the absolute value of the kernel kz equals 1 over pi z diverges. In fact, the integral over any interval from minus epsilon to epsilon also diverges. In contrast, an integral operator would be defined by integrating a function against some integrable kernel. For example, the convolution of a function f with an approximate identity psi delta gives an integral operator, which we have used several times on the course. As you might already guess, the theory of singular integral operators gets fairly technical, but these operators arise naturally in many applications, especially in the theory of partial differential equations. Given a singular integral operator, the fundamental question is, when is it bounded? In general, you can pick any pair of function spaces and ask whether the operator is bounded from the first space to the second space. For the Hilbert transform, and during this lecture, we will only be concerned with the question whether the Hilbert transform defines a bounded operator from the space Lp to itself for some exponent p between 1 and infinity. We will prove a positive answer in the case where the exponent p is 2. This is the content of theorem 5.1. Namely, the operator h is bounded on the space L2 of R. In fact, the operator h is an isometry on L2. The L2 norm of hf equals the L2 norm of f for every function f in L2. In general, an isometry from an infinite-dimensional space to itself need not always be invertible. But the Hilbert transform is also invertible on L2. We will leave this extra detail as an exercise. To summarize, the Hilbert transform is an invertible isometry from L2 to L2. What about other LP spaces? The proofs already go beyond this course, but here are the right answers. The Hilbert transform is a bounded map from LP to itself whenever the exponent p is strictly between 1 and infinity. The same is not true for the endpoint exponents 1 and infinity. The proof of the positive result uses a technique known as Calderon-Zygmund theory. Perhaps surprisingly, the proof of the boundedness on more general LP spaces uses the boundedness on L2 as a black box. So if you want to study the action of the Hilbert transform on more general LP spaces, you will still need to start by establishing theorem 5.1. We then start discussing the proof of theorem 5.1. The proof is based on the Fourier transform, and we outline the idea right away. Most of the details will be contained on the next lecture. The plan is to verify that the kernel 1 over pi z defines a tempered distribution. K is an element of S prime. Since K is not a locally integrable function, the details are not entirely straightforward, and that's why we've still placed the quotation marks around the statement that K belongs to S prime. For the time being, let me just say that there is a reasonable way to associate a tempered distribution to K, which we will see a bit later, but this way is more complicated than you'd expect. Nevertheless, we denote this tempered distribution by K. Then, to be precise, the Hilbert transform of a Schwarz function phi is defined as the convolution of this tempered distribution with phi. By the results of the previous lecture notes, the convolution between a tempered distribution and a Schwarz function is an infinitely differentiable function of polynomial growth. So, in particular, the Hilbert transform of a Schwarz function can be initially defined as an infinitely differentiable function of polynomial growth. Moreover, by theorem 4.22 on the lecture notes, the Fourier transform of this function viewed as a tempered distribution is given by multiplying the Fourier transforms of phi and the distribution associated with K. This is a nice abstract formula, but to make any practical use of it, we need to compute the Fourier transform of the distribution K explicitly. The answer turns out to be very simple. The Fourier transform of K is the tempered distribution represented by the signum function. I prefer to call this function signum instead of sine, because sine sounds exactly the same as sine, and it would be very confusing to talk about both functions in the same sentence. We denote the signum function by sigma. Sigma of x equals 1 for positive values of x and minus 1 for negative values of x. The signum of 0 is defined to be 0. Now, more precisely, the Fourier transform of K is the tempered distribution represented by the signum function multiplied by the constant minus I. This means the usual thing. The Fourier transform of K is another tempered distribution whose value at the Schwarz function phi is obtained by integrating phi against the function minus I times sigma. Even though there will be some technical difficulties in associating a tempered distribution to the kernel K, due to the fact that K is not absolutely integrable, there are no difficulties whatsoever in defining the Fourier transform. The Fourier transform is simply an L-infinity function whose absolute value is identically 1 Lebesgue almost everywhere. Once we get this far, the proof of theorem 5.1 will be quite simple. We only need to use the Plancherel identity and the fact from theorem 4.22 that the Fourier transform turns convolutions into products. To prove theorem 5.1, we need to fix a Schwarz function phi, and we need to compute the L2 norm of h phi. This equals, by definition, the L2 norm of the infinitely differentiable function k convolved with phi. Then we use the Plancherel identity, which states that the Fourier transform is an isometry on L2. The L2 norm of k convolved with phi equals the L2 norm of the Fourier transform of this convolution. Next, we use theorem 4.22 to conclude that the Fourier transform of the convolution equals hat phi times hat k. Finally, it remains to plug in the Fourier transform of k. This was an L-infinity function whose absolute value is the constant 1 Lebesgue almost everywhere. Simply by pulling this constant absolute value outside the L2 norm, we end up with the L2 norm of the Fourier transform of phi. At this point, we may use the Plancherel identity once more to find the L2 norm of phi itself. This concludes, at least formally speaking, the proof of theorem 5.1. There are a couple of fishy points about this argument. First of all, we still haven't defined the tempered distribution associated with K carefully, so even the very definition of the Hilbert transform remains shaky. Second, once we have solidified the definition of the Hilbert transform, we still need to compute the Fourier transform of k and show that it equals a constant times the signum function. There is also a smaller issue in the formal computation above. We have only proved on previous lectures that the Blancherel formula is valid for L2 functions, but here we don't know a priori that k convolved with phi is an L2 function. In fact, that's precisely what we are trying to prove. It turns out that there is no circular reasoning here, and the Blancherel identity can also be used in this situation. We will return to all of these points on the next lecture. This completes lecture number 23 on the course Introduction to Fourier Analysis.